Okay, this is where we left off yesterday. So today we are going to talk about properties and changes in matter. Extensive properties versus intensive properties. Extensive, so if you think of exit or outside, extensive properties are going to depend upon the amount of matter that is present. So for those kinds of properties, some examples would be volume. How much matter is present would determine your volume. It would also determine your mass. Just like when we had the balloon, when we increased its volume with air, it had more mass. The amount of energy in a substance is also an extensive property, and we'll talk about this. I had brought the ice in today to show you, but that's something I'll show you again tomorrow with the amount of energy. Intensive properties, then, do not depend on the amount of matter present, and the melting point, the boiling point, and the density are all three intensive properties. Melting point does not matter how much ice you have, it always melts at 0 degrees Celsius. Boiling point, no matter how much water you have, it will always boil at 100 degrees Celsius. Density, you can have a little piece of lead or a great big piece of lead. It has the same density. So those are all properties that are intensive. Now, the ability to conduct electricity. Copper wire has a good ability to conduct electricity, and so it doesn't matter how much copper wire you have, it still conducts electricity. Ability to transfer heat. You know that if you grab onto a metal spoon that's been sitting in a boiling hot water bath, it's going to be hot, whereas wood will not. So those would be the properties of those substances without. Okay, so it cut off and it's restarting here. But these are properties. So the amount of energy as heat, it doesn't matter how much you have, it will still transfer energy as heat either way. So properties of matter. Here is the chart, and I'm just going to pause and let you read it yourself. And these are all things that we will discuss more, and you should take note of the different properties.
Extensive properties depend on the amount of matter that is present. For example, the volume of water in a small beaker is 25 milliliters, and the mass of that water is 25 grams. The volume of water in the large beaker is 100 milliliters, and the mass of that water is 100 grams. Intensive properties do not depend on the amount of matter present. For example, at standard pressure, the boiling point of water is 100 degrees Celsius, no matter how much water is present. Similarly, at 4 degrees Celsius, the density of water is 1 gram per milliliter, regardless of how much water is present.
So physical properties and physical changes. A physical property is a characteristic that can be observed or measured without changing the identity of the substance. Melting point and boiling point are examples of physical property. Also, if you take a piece of paper and you just rip it up, you still have paper. That's just physically changing it. If you crumple the paper, it's still paper. So what we did was physically change that substance, that paper. So physical change is a change in a substance that does not involve a change in the identity. And grinding, melting, boiling, cutting, scrunching up paper, all of those are physical changes. A change of state is a physical change. So when we go from a solid to a liquid or a liquid to a gas, we are just changing its state of matter. It's still, if we melt water, if we have ice and we melt it, it's still water. So the state of matter, if it goes from a solid to a liquid or liquid to a gas, it is still that it's still that substance. It's just in a different state of matter. So what are the different states of matter? Solid state. This is where matter has a definite volume and definite shape. In the liquid state, It has a definite volume but indefinite shape. It will take the shape of the container. In the gas state, matter does not have a definite volume or a definite shape. It'll just fill whatever container you put it in. Plasma is the most abundant of all of the states of matter in the universe. And that's because of all the sun and the stars. So it is high temperature physical state of matter where the atoms are going to lose electrons, and those are the particles, some of the particles that make up the atom. So we'll get more into the parts of the atom, but plasma is at very high temperatures.
A solid has definite volume and definite shape. The particles of a solid vibrate in fixed positions and are held in place by strong, attractive forces between them. The liquid has a definite volume but not a definite shape. The particles of a liquid have a range of movements that allows them to slide past one another. A gas does not have a definite volume or shape. The particles of a gas move fast enough to overcome nearly all of the attractive forces between them. Gas particles move independently of one another. A solid has definite volume and definite shape. The particles of a solid vibrate in fixed positions and are held in place by strong, attractive forces between them. A liquid has a definite volume but not a definite shape. The particles of a liquid have a range of movement that allows them to slide past one another. A gas does not have a definite volume or shape. The particles of a gas move fast enough to overcome nearly all of the attractive forces between them. Gas particles move independently of one another.
So here we see water in the three states of matter. And I want you to look at the water molecule in the solid state. Here you'll see these air pockets. When water freezes, it freezes with air trapped in the molecules. So that air makes water less dense because it's trapped inside there. And that's why ice floats. And then once it melts, those air pockets, the water molecules are able to get a little closer together, and those air pockets are not as precise and not as full. So therefore, when we go to a gas, you see there's lots of air and space between the molecules, and that is the least dense. So water kind of defies the becoming more dense as we become solid state. So chemical properties and chemical changes. The chemical property relates to a substance's ability to undergo changes that transform it into different substances. So a property, chemical property in my words would be how a chemical reacts with another chemical, how one substance reacts with another substance. That's what a chemical property is. We define it by how it reacts with something else. A change, when we make the change, that is a chemical change. So when we put water with sodium, there is a chemical change. You will observe a chemical reaction. And there is evidence of chemical reactions, and we'll talk about those. I don't believe these little movies work on this computer. Not going to work. So here we'll go back. So chemical properties and chemical changes. Reactants then are the substances that you put together. The products are the things formed, the substances formed from the chemical change. We have reactants, they react, and then we get the product. So if we put carbon and oxygen together, we form carbon dioxide. And so the chemical equation looks like this. Carbon plus oxygen yields carbon dioxide. Here are some different ways you know that a chemical change is taking place. And when we do our reactions tomorrow, I want you to try to be able to list this evidence. So when acetic acid is put in vinegar, we make carbon dioxide. So a gas is given off. In this second example, it's not as evident, but you see we're putting a clear liquid in a clear liquid, and it's making a yellow powder. You can't tell that it's a powder, but it will settle out eventually. And I will also show you this, and that is called a precipitate. When aluminum reacts with iron oxide in a clay pot, energy is released as heat and light. This is a little bit more, we won't do this example, but we'll do another one where energy is released tomorrow. So in this last one, phenolphthalein is added to ammonia and it's dissolved in water, and there's a color change. So we observe color changes, energy release or energy absorption, and we observe precipitates, and we also observe gases being formed. That's what I want you to look for when we do the chemical reactions tomorrow. Electrolysis of water. If you remember today in class, this apparatus was actually sitting on my desk, and we can hook up, we'll get this tool, this machine out, and we will add electricity to water, and we will do this experiment as well. We'll pass an electric current through the water, causing it to break down into its components, which is H2 and O. And when it breaks down, it'll be H2 and O2. Oxygen never is by itself, and neither is hydrogen. So we will do that in class as well, but that is a chemical reaction. How does water react with electricity? This experiment, when you put mercury oxide and you heat it, then you make a new substance. So it takes a lot of heat. I'm not sure if we'll do this one tomorrow, but we will do some other ones throughout the year.
The ability of an iron nail to be bent is a physical property called malleability. The rusting of iron is a chemical change. Iron's reactivity with oxygen to form rust is a chemical property. The food coloring in this water is red. Color is a physical property. Adding bleach to the solution changes the chemical composition of the dye, and it is no longer red. The ability of bleach to make other substances colorless is a chemical property.
Energy and changes in matter. So one of the evidence of a chemical reaction is energy, either being released or absorbed, and we'll show both of those tomorrow. Energy is always involved when physical or chemical changes occur. So energy can be seen as heat, light. Energy can be absorbed or released in a change. It is never created or destroyed, which leads us to the law of conservation of energy. When you conserve something, you never destroy it. It's only changing form. So we change form of energy. So here is what we call a bubble chart or a mind map of all of the different breakdown of matter. So classification of matter. And I think we'll draw this together in class and discuss this. I think this is where we'll stop for tomorrow, or for tonight, and then we'll discuss the homogeneous versus heterogeneous when we discuss that. So that's it for today. You are a couple minutes short of the limit.